So if we're going to use Newton's quotient to find the derivative of this, we can write out the formula for Newton's quotient, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. And then you've got to figure out what f of x plus h is and what of f of x is. Well, f of x is right here, so you can just plug that in. But f of x plus h, you might have to go off to the side and multiply it out. So you plug in x plus h where the x was, multiply it out, combine your like terms, and then we rewrite that in as well. Now our goal when finding the derivative using the definition is to evaluate the limit. Evaluating the limit right now, if I would plug in 0 for h, I would divide by 0. So that's a bad thing. So we simplify the equation, and on the top, the top equation simplifies to just 6xh plus 3h squared. And you might see already that you could divide everything by h now. But you might even want to factor that h out, so you can really see that you could simplify both of those h's. And then once those h's are simplified, you can now apply the limit, which means you plug in 0 for h, and the derivative for this one is 6x. What does that mean? Okay, we started off with 3x squared plus 4. That's something that you know how to graph. It's a parabola with a vertex at 0, 4, going up like this. If you picked a point on that parabola, for example, on that parabola you have the point 1, 7. And if I drew the tangent line at that point, I could say the slope of that tangent line is 6, because I could plug in the value of x equals 1 into my derivative equation, and I now know that if I drew a tangent line at that point, my slope would be 6. A little review of the definition. Remember that the definition was making a secant line turn into a tangent line, where if we zoomed in to this little point here, we'd imagine a tiny little triangle where we had h here, and this would be f of x plus h for a y value here, and f of x as a y value there. And as we bring those things closer and closer together, it makes that tangent line. As we apply the limit, it makes the tangent line. And using the definition of the derivative, what we get is we get an equation that tells us every single slope, no matter where we are on that parabola. For example, on the vertex is a really easy one to see that it should be a horizontal line. The slope of a horizontal line would be 0. Plug in 0 for x, and sure enough, 6 times 0 would be 0. Take another point. If you plugged in -2, you would get in the original equation -2, 16. What is the slope of this line going to be? -12. And we can get that from the derivative equation. So what the derivative equation does is it finds the slopes of all the lines of every single tangent line, no matter where you are on the curve. So here's our second one. We're going to use the definition of the derivative again for x cubed plus 1. Once again, we're going to expand f of x plus h. Now it's x cubed, so x cubed plus 3x squared h plus 3x h squared plus h cubed. You could get that from your binomial expansion in grade 12. You could use Pascal's triangle to get the coefficients of 1, 3, 3, 1. Or you could just write out x plus h, x plus h, x plus h, and multiply it all out. So it's a little bit time consuming sometimes. But then we can apply the definition. So you put f of x plus h in, which we expanded up above, minus f of x, all divided by h. And again, you're going to need to simplify this to see if you can cancel out an h. One thing you're going to start to notice in these equations is whatever you started with to begin with, which is x cubed plus 1, and you're subtracting that. Notice that you have an x cubed here that cancels out with that x cubed. Notice that you have a 1 here that's going to cancel out with the other one. And what ends up happening is you're left with terms that only have the h in them. If that's the case, you can factor an h out of the top and then divide and simplify. And then you're no longer dividing by 0, so you can apply the limit, plug in 0 for h, everything goes away, and we get 3x squared. How long do you think this question would take, time-wise? Like 4 minutes, 5 minutes? Okay. Later on in this unit, we're going to find, if this question takes 5 minutes, later on in this unit, we're going to find a technique that's going to save you 4 minutes and 55 seconds. Whew. Really. You'll be able to do this question in 5 seconds. That's how quick we're going to be doing some calculus. Okay? You're just going to see x cubed plus 1, and you're going to be able to say, I know the derivative is 3x squared, without having to do all this. Okay? That being said, we do need to practice working with the definition of the derivative. You're almost always asked a question that shows, do you understand how the definition of the derivative works and how to use it to find a derivative? So try this one on your own. Figure out what f of x plus h is, plug it in, and notice which things cancel out. And then from there, factor out your h and simplify it, apply your derivative, and you get 10x minus 2. Once again, you're going to be able to, if this one was a little bit longer, you're going to be able to do this one in 5 seconds as well. You're going to look at the original equation and say, oh, the derivative is 10x minus 2. Then when finding out exactly what it is when x is equal to 2, you can just plug in 2 into your derivative equation and say the slope will be 18, the slope of the tangent line will be 18 when x is equal to 2.